Hi, my name is Bennett, and this is my presentation on insertion sort. So insertion sort is a sorting algorithm, which means it will sort a set of numerical data that is given to it in an argument. And basically, it will go through an array starting at index 1, which is the second index, 5 in this case, and compare the value at the index it is looking at to all the values that have an index before that index. The data at the index that you start at will be inserted into the correct position in between the values that are directly less than and greater than itself. So for this set of data, it will start at 5, and 1 is less than 5, so it won't do anything. But it'll go to the next data, which is in index 2, which is 3, and it'll look at the data before it, which is 5. And because 5 is greater than 3, it will insert 3 before 5 and after 1, keeping the sort. And it'll go through the whole data set doing this until all the data is sorted. So this is pseudocode for insertion sort, which is basically just, what I was explaining before. So it'll go for every I in the list, it will go through every index before that index, and if the index before that index is greater than the index you started at, it'll insert the data you started at before the data that is greater than itself. So the runtimes for insertion sort, the worst runtime is going to be O of n squared, because for every data that you're looking at, it has to go through the whole data set. So basically you're going through the whole data set for every data that you look at. So that would make this O of n squared. The best case for insertion sort can be O of n, but this is very rare, and that only occurs when every data value only needs to be moved into the space directly behind it, which would mean that it would only go through the data one time instead of going through the data once for every data that it's looking at. Depending on how the insertion is handled, the runtime could increase because the index of every data after the insertion needs to be increased by 1. So depending on how you handled that, you could make it a lot worse because you might have to go through the data a whole extra time to update all the indices, but there might be a way to handle it differently that could fix that issue. Is it stable? Insertion sort is stable because it will go through values until it finds a value greater than the value the index starts at. So if it sees a value that any data will not have to pass over a data that is equivalent to the data that it's looking at. So if you have the data 24 at index 10 and there's another data 24 at index 7 directly before a data 27 at index 8, the algorithm will insert the data from index 10 in between index 7 and index 8, and it maintains the order that the equivalent data started in. Instability happens when you're basically changing the order of the data of equivalent data in the set, which would mean that if the data 24 at index 10 was inserted at index 6 before data 24, before the data 24 that was already before it. Memory use in insertion sort, it could be in place because really all you're doing is you're swapping two data. But basically, if the updating all of the indexes after the data that you insert, that could take more memory than just one memory address. So that's something that would have to be handled separately. Insertion sort can be used in conjunction with jort sort. So this is something I found online when I was researching sorting algorithms, and I've decided this is the best way to do sorting because it really just says that it checks the data, and if it's not sorted, then it tells you it's not sorted and you have to fix it. Really what it's supposed to be used for is so that the programmer can sort all of the data by hand, and really that's the way it's supposed to be. That's the way that nature intended, but really, if you wanted to, you could use insertion sort to help you out with that and let your computer do the job for you. So the takeaways from this, from insertion sort, basically it will sort data by going through every index in a list and then comparing the data at every index before that index until it finds data that is less than the data it started with, at which point it will insert the data directly after the index with a smaller data. This is actually supposed to be greater. Basically, so it goes through and it inserts data directly where it's supposed to go for every data set or for every data index. Insertion sort will usually have a runtime of O(n squared, which is the worst runtime that is reasonable for a sorting algorithm. I mean, really you could have worse than O of n squared, but you wouldn't want to do that because there are a lot with better runtimes. And really O of n squared is the worst. So you could have a sorting algorithm with a lot better than that, but if you really wanted to use insertion sort, you could. This algorithm is stable, meaning it maintains the order of equivalent data in the set, which is a good thing because you're not you're not doing more than you have to, really. If it was unstable, then you're sorting around data more than really is necessary. But this algorithm is stable, which semi-justifies its terrible runtime. The memory use of insertion could be in place, but different variations could possibly use more data if perhaps you were updating all of the indices by a different method, by storing all of those extra indices as different memory values. And insertion sort will probably sort your data for you, but real programmers will sort a data set manually as nature intended, as like sorting rocks of different sizes, as we've done since the olden days. So that's my presentation, and I hope you liked it, and I'm glad I took this class. So thank you very much.